What's up, bitches? So, today, we're gonna look at Fourier series. And the question I want to answer is, what Fourier series approximates t squared on the interval from 0 to 2 pi with a 2 pi period? So, what we need to know is that a Fourier series approximates a function in this manner. What you do is you take a0 divided by 2 and sum up all these terms where n goes from 1 to infinity. And as we see here, we increase the harmonic of the sine and cosine parts every time we do so. Omega 0 is the base frequency, which is 2 pi divided by the period. So basically, when n increases, we increase the number of periods that the sine function does on that domain and on that period. And the first period of the sine function is the period of the function it approximates. So, what do all these variables mean? Well, a0, I don't define just a0. We can find it from here. So when n equals 0, we see that it will be cosine of 0, which is 1. So all of this will perish, and we'll end up with the integral of ft over 1 period dt. And it's similar for the bn part, except we have sinus instead of cosinus. Now I will link to a visualization of the Fourier series that I find really helpful. It's gonna be a fucking mind blow, like fireworks and sparks and shit. But calm your tits. First, we're gonna solve this problem. So we can start by finding a0. So a0, as I explained earlier, is the integral from 0 to 2, because that's the interval we chose up here. 0 to 2. Bam, bam, bam. So, of the function ft dt, remember that the cosine part perishes since n is equal to 0. So, in this case, it's the integral of t squared dt from 0 to 2, which is equal to t cubed over 3, evaluated from 0 to 2. And what's all this then? 2 pi, obviously. Remember that it's 2 pi and not just 2. My bad. So, at the 0 part it will vanish, it will be 0, so we basically end up with 8 pi cubed divided by 3. I just remember that I forgot the 2 divided by the period part. That's no biggie. 2 divided by t, 2 divided by t, 2 divided by t. Poker face, nailed it, close enough. Times 1 over pi, if we plug the values in, which is equal to 8 pi squared over 3. So here we have our a0 value. And now for our an value. It's a little bit more complicated. We get 2 over the period times the integral from 0 to 2 pi of t squared times cosine of nt. Remember, omega 0 is 2 pi over t, and t is 2 pi. 2 pi over 2 pi is simply 1, so it kind of perishes as well. Which is equal to yes, this will be equal to 1 over pi times the integral from 0 to 2 pi of t squared cosine of nt dt. Of course, dt here as well. So we can either look this up in a formula booklet to save time, or we can just I'm gonna show you which formula I'm going to use because we have limited time. So x squared cosine of ax is equal to 1 over a cubed times negative sine 2ax plus 2ax cosine ax plus a squared x squared sine ax. And if you do this integral, you find that an is equal to 4 pi over n squared. And the same thing for bn. But we use another formula. I cannot do very long videos because they take up a lot of memory. So if we look here, we're going to end up with practically the same thing for the sinus part. Beautiful formula there. And what we're going to get is, so I made a little typo there, or righto is a better word for it. So what we end up with is these two values for an and bn. And so when we plug this into the formula, we get that t squared is approximately 4 pi squared divided by 3 minus wait. Now I gotta think here with the if we factor out the 4. No, but it's pluses, of course. Plus 4 times the summation from n equals to 1 to infinity an. So cosine of n pi, remember omega 0 is 1 since it's 2 pi periodic, over n squared minus pi over n sinus of n pi. Don't forget your hard brackets. That was easy. And obviously we end this video with a quick scope. Get wrecked, mate.